Relational algebra is like a set of LEGO bricks that let us build queries on a table called a relation. Each brick select project join division does one simple job, but when we snap them together we can ask very complicated questions. We need these operators because raw data is often huge, and messy. The operators let us filter rows, pick only the columns we care about, combine information from different tables, and find all of these patterns. Think of a school. You have a list of students, a list of classes, and you want to know which students take every math class. Without a systematic way, the operators you would have to manually scan the lists every time. Relational algebra gives a precise, mathematically sound language that underlies SQL and helps the database engine decide the fastest way to get the answer. The selection operator is written with the Greek letter sigma sigma. Formally, if R is a relation, a set of tuples, and phi is a Boolean condition, for example, age greater than 18, then sigma sub phi of R equals open brace T in R such that T satisfies phi close brace. In words, sigma picks out every row T from R that makes the condition true and returns a new relation that contains exactly those rows and all their columns. The result of sigma is always a relation with the same schema, same column names as the input. Symbolically, we write the condition as a subscript of sigma. For example, sigma sub salary greater than 50,000 of employees. Imagine a table books with columns ISBN, title, author, year, price. We want all books published after 2015 that cost less than $20. The selection condition phi is year greater than 2015 and price less than 20. In relational algebra notation, sigma subscript year greater than 2015 and price less than 20 close parenthesis books. Mathematically, let B be the set of all book tuples. The result is the set of B and B such that B dot year greater than 2015 and B dot price less than 20. If B contain the tuples 001 A Alice 2016-15, 002 B Bob 2014-18, 003 C Cara 2018-22, then the selection would return only the first tuple because it is the only one satisfying both parts of phi. This is exactly what a child could picture as pick the books that are new and cheap. The projection operator is written with the Greek letter pi. It reduces a relation to only the columns we care about. Formally, if R is a relation with attributes a 1, a 2, and so on an n, and we want a subset of attributes X equals the set of a I1, a I2, and so on a Ik, then pi sub X of R equals the set of T sub X such that T is an element of R. Here T sub X means the tuple formed by taking only the values of T for the attributes in X. Duplicate rows are eliminated because a relation is a set, not a multiset. The result schema is exactly the list X. Symbolically, we write the list of attributes as a subscript, for example, pi subname salary of employees. Consider the same employees table with columns M pi D, name, department, salary. If we only care about the list of distinct departments, we use pi subscript department of employees. Mathematically, let E be the set of employee tuples. The projection yields the set E dot department such that E is in E. If E contains the records 1 Anna HR 50,000, 2 Bob IT 60,000, 3 CIA HR 52,000, the projection returns the set HR and IT. The duplicate HR disappears automatically. A child could think of this as take a big picture and cut out only the colors you want. If the same color appears many times, you only keep one piece of that color. Joins combine rows from 2 or more relations based on a relationship between their attributes. Theta join, pronounced theta join, dash the most general form. Given relations R and S and a condition theta, the result is R join sub theta S equals the set of T sub R join T sub S such that T sub R is in R, T sub S is in S, and T sub R and T sub S satisfy theta. The condition theta can be any Boolean expression. For example, r.id equals s.emp underscore id and r.date greater than s.start underscore date. Equijoin, a special theta join where theta is only equality comparisons. For example, r.id equals s.id is written as r join sub r.id equals s.id sub s. Natural join and equi-join that automatically matches all attributes with the same name and then removes the duplicate columns. It is denoted R join S. Formally, R join S equals pi of the attributes of R union attributes of S applied to sigma of R dot common equals S dot common of the Cartesian product of R and S. The common attributes are those that appear in both schemas. Outer joins, unlike inner joins, which keep only matching rows, outer joins also keep non-matching rows and fill missing values with null. There are three kinds. Left outer join R left outer join S keep all rows of R. If a row has no match in S, attach nulls for S's columns. Right outer join R right outer join S keep all rows of S. Unmatched R rows become null. Full outer join R full outer join S keep all rows from both sides. Unmatched rows get nulls on the opposite side. All joins start from the Cartesian product of R and S, and then filter sigma and possibly project pi to shape the final relation. Suppose we have two tables: students with attributes student ID and name, enrollments with attributes student ID and course ID, courses with attributes course ID and title. We want the names of students who are enrolled in the course title databases. Step 1. Find the course ID for databases. Pi subcourse ID of sigma subtitle equals databases of courses yields the set containing C42, assuming C42 is the identifier. Step 2. Join students with enrollments on student ID. Students join on students.student ID equals enrollments.student ID with enrollments. Step 3. Join the result with the set containing C42, treated as a one-row relation on course ID. The expression is the join of students and enrollments. Then join on enrollments.course ID equals C42.course ID with sigma, where course ID equals C42 of courses. Step 4. Project only the name attribute, pi subname of the previous result. Putting it together in compact notation. Pi subname of open parenthesis students join on students.student ID equals enrollments.student ID with enrollments close parentheses. Join on enrollments.course ID equals courses.course ID with sigma, where title equals databases of courses close parentheses. If the tables contain the following rows: students 1, Anna and 2, Ben enrollments 1, C42 and 2, C99. Courses C42, databases and C99, algorithms. The calculation yields the single name Anna because only Anna is linked to the database's course. Outer join example, to list all students and the course they take, showing null when a student is not enrolled. Students left outer join enrollments. Here every student appears. If a student has no matching row in enrollments, the course ID column becomes null. Explanation: division answers questions of the form find the x values that are related to all y values in a given set. Formally, if R of a b and S of b are relations, the division R divided by S produces the set of a such that for all b in S, the pair a b is in R. In words, give me every value of attribute a such that for every b value present in S, the pair a b appears in R. It can be rewritten using basic operators: R divided by S equals pi sub a of R minus pi sub a of open parenthesis pi sub a of R cross S minus R close parenthesis, where minus is set difference. Example: suppose we have a relation grades with attribute student and course that lists every course each student has passed. Let S be the set of required core courses: math, English, science. We want the students who passed all core courses. Required equals pi subcourse of sigma, where course in math, English, science applied to grades. Result equals grades divided by required. Mathematically, result equals the set of S such that for all C in the set math, English, science, the pair S, C is in grades. If grades contains Anna, math, Anna, English, Anna, science, Ben, math, Ben, English, then the division returns Anna because Ben is missing science. This set-based viewpoint helps a child picture a checklist: a student gets a gold star only if they have a sticker for every item on the list. Explanation: translating the algebraic expressions into SQL is straightforward because SQL was designed to implement the same ideas. Selection sigma subcond of R becomes select all from R where condition. Example: Sigma sub age greater than 18 of people becomes select all from people where age greater than 18. Projection pi sub adder 1, adder 2 of R becomes select distinct adder 1, adder 2 from R. Example. Pi sub name, salary of employees becomes select distinct name, salary from employees. Theta join or equijoin of R on R dot id equals S dot emp id with S becomes select all from R join S on R dot id equals S dot emp id natural join of R and S matching same named columns becomes select all from R natural join. S left outer join of R and S becomes select all from R left outer join S on R dot id equals S dot id. Division R divided by S expressed with not exists or having count all. Select R dot A from R as R group by R dot A having count distinct R dot B equals the count of all rows from S. The query groups by the A attribute and keeps only those groups that are linked to all B values present in S. Putting the earlier student and course example into SQL. Select distinct S dot name from students as S join enrollments as E on S dot student ID equals E dot student ID join courses as C on E dot course ID equals C dot course ID where C dot title equals databases. And the division example, students who passed every core course. Select G dot student from grades as G where not exists a subquery selecting all from required core, as R where not exists a subquery selecting all from grades as G2, where G2 dot student equals G dot student, and G2 dot course equals R dot course. These translations show that relational algebra is the theory while SQL is the practical language that database engines understand.